Acid-base, Part 6, Buffer Solution. Exercise 35. Consider 1 liter of buffer solution NaHSO3 of concentration 0.1 mole per liter. Calculate the pH of this solution. NaHSO3 is a strong electrolyte since no value of Ksp of salt is given. So NaHSO3 dissociates completely to Na plus and HSO3 minus. Na plus in the solution is a spectator. HSO3 minus is ampholyte. So the pH of NaNHSO3 solution is the pH of the ampholyte HSO3 minus. So pH equal half pKa1 plus pKa2 equal 4.6. So we add to the preceding solution without variation of volume 0.05 mole of the strong base NaOH. So we obtain a solution S. Calculate the pH of the solution S. HSO3 minus is an ampholyte that plays the role of acid in a couple and base in another couple. So when you add OH minus, we will have reaction between OH minus and HSO3 minus, and this reaction is complete since the difference of pKa is greater than 4, or K of the reaction is greater than 10 to the power 4, or 10 to the power 4 quantitative, or 10 to the power 6 complete. So the initial number of mole of HSO3 minus is equal to the concentration times volume equals 0.1 mole, and the number of moles of OH minus equals 0.05 mole. So we write the reaction, and we construct the table of conversion at T equals 0, 0.1, 0.05, 0. This reaction proceed till equilibrium, which is T equal infinity, since K of the reaction equal 10 to the power 6.8 greater than 10 to the power 6, so the reaction is complete. OH minus is limiting, so OH minus is practically equal to 0, and HSO3 minus equals 0.1 minus 0.05, so we have 0.05 mole of HSO3 minus and 0.05 mole of SO3 2 minus. If they ask us to calculate, for example, the quantity of OH minus or the concentration of OH minus at T equal infinity, so we have to calculate this value, which is practically 0. To note that epsilon is only calculated if they ask us to calculate the concentration of OH minus at T equal infinity. So the reaction, after the reaction is complete in direction 1, it will return a little bit in direction 2, so we will have 0.05 minus epsilon of SO32 minus, plus epsilon of OH minus, and 0.05 plus epsilon of HSO3 minus. We can neglect epsilon with respect to 0.05 and epsilon to respect to 0.05 in case of HSO3 minus. By applying Kr of the reaction equal concentration of the product divided by the reactant, we can calculate epsilon. So in the final solution, we will have HSO3 minus 0.05 mole and SO32 minus 0.05 mole. So we will have exchange between the acid and its conjugate base till the equilibrium. But since the acid and its conjugate base are of weak behavior, so practically the new number of moles after exchange are the initial number of moles we start with. So in the solution, we have practically at equilibrium HSO3 minus 0.05 mole and SO32 minus 0.05 mole. So we can apply Henderson. pH equal pKa of the couple involved, which is pKa2, plus log base SO32 minus at equilibrium divided by the acid at equilibrium. So equal pKa2 plus log number of moles, and the number of moles are practically the initial, so 0.05 divided by 0.05 log 1 equals 0, and the pH equal 7.2, which is the pKa of the couple SO32 minus HSO3 minus, so we have a buffer solution. We add to the solution S without any variation of volume 0.05 mole of HCl. Calculate the pH of the new solution. So the solution S initially contains HSO3 minus and SO32 minus of equal number of moles. When we add HCO plus, according to gamma rule, we will have two reactions. The first is between HCO plus and SO32 minus. The second is between HCO plus and HSO3 minus. So we write the two reactions and we calculate K of the reaction. HSO3 minus plus HCO plus gives SO32 minus plus H2O. K of the reaction 1 calculated is equal 10 to the power 2. Reaction 2, SO32 minus plus HCO plus gives HSO3 minus plus H2O, and K of the reaction 2 equal 10 to the power 7.2. So K of reaction 2 is greater at least 100 times than K of reaction 1. So the reaction 2 is the first. So it will start and then reaction 1 will start. It's not necessary in this problem to calculate K of the reaction to compare the sequence. We can say the greater gamma will start the first. So the gamma in red is less than the gamma in green. So the reaction between SO32 minus and HCO plus will start the first. So the new solution contains HSO3 minus 0.05, SO32 minus 0.05, and the number of mole of HCO plus equal the number of mole of HCl added equal 0.05. We write the reaction between SO32 minus and HCO plus, and we calculated, according to the table of conversion, the number of moles at equilibrium. As we observed, in this reaction, we don't have excess, so SO32 minus and HCO plus reacted completely, and HSO3 minus is equal to 0.05 initial plus the 0.05 formed. If they ask to calculate the concentration of SO32 minus or HCO plus remained, we have to study the reaction in the inverse direction and to calculate epsilon, and this is not the case of the exercise. So in the final solution, we have only HSO3 minus, which is equal to 0.1 mole, and as you know, HSO3 minus is an amphoteric substance or ampholyte, so the pH is directly applied equal half pKa, where HSO3 minus is acid, plus pKa, where it's a base. So half pKa1 plus pKa2 divided by 2, and the pH is equal to 4.6. Exercise 36. 0.1 mole of formic acid and X mole of sodium formiate are introduced into 1 liter of water. The pH of the solution obtained is 3.74. What is the value of X? So when we mix HCOH and HCOO minus, we have a solution containing the weak acid and its conjugate base. The number of mole of the acid 0.1 mole, that of the base equal X mole. The behavior of HCOOH and HCOO minus is weak. So between HCOH and HCOO minus, the exchange till the equilibrium will be very weak. So the concentration or the quantities at the new equilibrium are practically equal to the initial. So pH equal pKa plus log HCO minus divided by HCOH at equilibrium. So pH equal pKa plus log concentrations initial. So pH equal pKa plus log number of mole HCO minus divided by HCOOH, since we cancel the total volume, and therefore 3.74 equals 3.75 plus log X divided by 0.1 mole, and by this way we can calculate X. So X equal 0.0977 mole equal approximately 0.1 mole. And since the pH of the solution is very close to the pKa of the couple, so we have the optimal buffer capacity. In part B, to the previous solution containing the acid and its conjugate base, we add water. What would happen to the pH of the solution? As we know, adding water did not affect the pH of a buffer solution, since the acid and its conjugate base will be diluted by the same way. Exercise 37. In 250 ml beaker, we introduce acetic acid, HCl, and NaOH and water. Calculate the pH of the solution. In this type of exercise, we add a base to two acids, so we will have necessary two reactions. The initial solution contains N-acetic acid 0.8 millimole, NHCl 0.2 millimole, and NOH minus equal 0.6 millimole. So according to gamma rule, we will have reaction between OH minus and HCO plus, and another possible reaction between OH minus and acetic acid. So we write reaction 1, HO minus plus HCO plus gives 2H2O, K of the reaction equal 10 to the power 14. So this reaction is complete. Reaction 2, OH minus react with acetic acid to acetate and water. K of reaction 2 equal 10.9.2, and this reaction is also complete. By comparing K of reaction 1 with K of reaction 2, we find that Kr1 greater at least 100 times Kr2. So the reaction 1 will start, and then the reaction 2 will start. To note that we can compare these two reactions since they have the same stoichiometry, and reaction 1 can be written HO minus plus HCO plus gives H2O plus H2O, so the stoichiometry is 1, 1, 1, 1, the same as reaction 2. We write reaction 1, HCO plus plus OH minus gives 2H2O. We put the initial values of the reactant 0.2 and 0.6. So HCO plus is limiting, and we have 0.4 millimole of OH minus in excess. This OH minus will be transferred to the reaction 2 with acetic acid. We have initially 0.8, and we have 0.4 remained from reaction 1, 0. At equilibrium, T equal infinity, since this reaction is complete, so OH minus is limiting, and we will have 0.4 millimole of acetic acid and 0.4 millimole of acetate. To note that if we want to calculate the concentration of OH minus at equilibrium, we have to use or to consider the inverse reaction, so to calculate epsilon. The new solution contains acetic acid 0.4 and acetate 0.4. I will not repeat the same as previous examples. Acetic acid and acetate are of weak behavior, so the exchange between them is very weak, and the number of moles at the new equilibrium is practically the initial number of moles. So pH equal pKa of the couple involved plus log concentration base divided by the acid at equilibrium, which is equal to the initial. So pH equal pKa plus log number of moles acetate divided by the number of mole of acetic acid. So plus log 1 equals 0, and the pH equal pKa of the couple equal 4.8. So we prepare a buffer solution of optimal capacity since the pH equal pKa. Exercise 41. Consider a mixture of a buffer solution A, which is 0.1 molar acetic acid and 0.1 molar acetate. Calculate the pH change in each of the following cases. We add 10 ml HCl 0.1 m. So before the addition of the acid, we have a buffer solution where the initial concentrations are equal to 0.1. So the pH initial is equal to pKa of the couple plus log acetate divided by the acetic acid at equilibrium. And the concentrations at equilibrium are practically the initial concentrations, since acetic acid and acetate are of weak behavior. So pH 0 equal pKa plus 4.76. When we add HCl to A, the acid will react with the base acetate. So the number of mole of H2O plus initial introduced is 1 millimole, and that of the acetate is equal to 10 millimole. We write the reaction and the table of conversion. This reaction is complete. Initially we have 10, 1, 10. HCO plus is limiting, so practically equal 0 or epsilon. And we have 9 millimole of acetate, and we have 1 mole formed of acetic acid plus the 10 millimole initially, so we have 11 millimole. So in the solution, we will have the acid and its conjugate base, and we will have exchange between this acid and this base. So the concentrations, by the same way, the concentrations at equilibrium are the concentrations obtained. So pH equal pKa plus log number of moles of acetate divided by acetic acid at the new equilibrium, which are the initially obtained at the first equilibrium, so equal 4.76 plus log 9 divided by 11 equal 4.67. So the variation of the pH is the pH after the addition minus the pH initial, so equal 4.67 minus 4.76, so equal minus 0.09, and therefore we have 9% variation of the pH after the addition of HCl. In other words, this buffer solution initially of acetic acid and acetate has consumed the addition of the acid strong HCl without significant variation of the pH. The same exercise, what would happen to the solution A when we add 10 milliliter of the base? In this case, the base will react with the acetic acid present. So before addition of NaOH, we have a buffer solution A of pH equal 4.76. When we add OH minus, the reaction taking place is between acetic acid and OH minus. We write the initial number of moles in the solution and the table of conversion according to initial number of moles till T equal infinity. So we have 10 acetic acid, 1 OH minus, and we have initially 10 acetate. OH minus is limiting, so equal epsilon, and we have 9 millimole of acetic acid and 10 plus 1 mole of acetate. By the same way, we have the acid and its conjugate base, so the pH equal pKa plus log base over acid equal 4.76 plus log 11 divided by 9 equal 4.85. So the variation of the pH is equal to the pH after addition minus pH initial, and in this case equal plus 0.09. So we have 9% variation of pH. In other words, the addition of 10 ml NaOH 0.1 molar was consumed by the buffer solution present without significant change of the pH of the buffer solution. The same exercise 41, part C. What would happen when we add 100 ml of water to 10 ml of HCl? Compare the results obtained in part C with the previous parts. So initially, before mixing, we have a beaker, for example, containing pure water, where the pH is equal to pKw divided by 2 equals 7. And in the second beaker, we have HCl solution of concentration 0.1 molar. This concentration is greater or equal 3.2 10 minus 7, so we apply directly the relation pH 0 equal minus log C0 equal 1. So we have two beakers, the first containing water of pH 7 and the second containing HCl of pH 1. Now what would happen when we mix water with the HCl? So we will have dilution of the HCl, and the C initial, V initial is equal to C final, V final. So the final concentration is equal to the initial concentration 0.1 times V initial 10 divided by V total, which is the V initial plus the volume of the water added. So the concentration, the new concentration equal 9.1 10 minus 3 m, greater or equal 3.2 10 minus 7. We apply the relation pH equal minus log C final equal 2.04. So the pH of water fall from 7 to 2.04, and the pH of HCl increase from 1 to 2.04. So the variation of the pH of HCl is 1.04, and the variation of the pH of water is minus 4.96. So as a conclusion, adding acid to pure water cause sharp change in the pH of both. But in case of the buffer solution, in part A, when we add HCl, we have 9% variation of the pH. And in the part B, when we add OH minus, we have also 9% of change of pH. So while adding acid or base to a buffer solution, this will cause slight change of the pH of this solution. Exercise 42, calculate the pH of a buffer solution as 0.2 molar NH3 and 0.2 molar NH4 plus. So the pH of a buffer solution is pH equal pKa plus log base over acid at equilibrium. The acid and the base are of weak behavior, so the concentrations at equilibrium are the initial concentrations. Therefore, pH equal pKa equal 9.2. We add to this buffer solution HCl 0.1 mole per liter. Determine the pH when the volume of HCl added is 100 ml. When we add HCl to a buffer solution, the acid will react with the base. So we have complete reaction with NH3. The initial number of mole of NH3 equal 20 millimole, that of HCO plus added equal 10 millimole. We write the reaction and the table of conversion. This reaction is complete. So initially we have 20, 10, 20. At T equal infinity, HCO plus is limiting. So we have 20 minus 10 equal 10 millimole of NH3 remained, and we have formation of 20 plus 10 equal 30 millimole of NH4 plus. So in the final solution, we will have a mixture of the acid and its conjugate base, and the exchange between them is very weak. So the concentrations at the new equilibrium are practically the concentrations or the quantities obtained in equilibrium 1. So pH equal pKa plus log number of mole ammonia divided by the number of mole of ammonium equal 9.2 plus log 10 divided by 30 equal 8.72. We repeat the same work but with the volume 200 ml. We write the table of conversion. So initially we have a 20, 20, and 20. 20 NH4 plus. In this case, we don't have limiting or excess. So NH3 will react completely with HCO plus to form 20 new mole of NH4 plus the initial 20 millimole present. So we have 40. So in the final solution now, we have NH4 plus where the number of moles equal 40 millimole. And the concentration is equal to the number of mole divided by V total, and the V total is equal to the 20 ml of HCl added and the initial 100 ml present, so equal 300 ml, and the concentration is 0.1334 molar. Since the number of mole is in millimole, so you can put the volume in milliliter. The pH of the new solution is the pH of the weak acid NH4 plus. So we return to the domain of validity of weak acid. We compare the initial concentration with 100 Ka, C0 greater or equal 100 Ka. So we can apply directly the relation pH equal half pKa plus PC0 or half pKa minus half log C, so equal half times 9.2 minus half log the concentration obtained, so equal 5.37. Exercise 42. To the solution obtained in part B, we add sodium acetate 3.2080 grams and no change of the total volume. Calculate the pH of the final solution. The solution B in B contains NH4 plus 40 millimole and the concentration is equal 0.1334. So we calculate the initial concentration of acetate the concentration is equal to the initial number of mole divided by the volume, equal mass divided by molar mass times V, equals 3.28 divided by 82 times the V total, which is 0.3. So the concentration equals 0.1334 molar. So in the new solution at T equals 0, we have NH4 plus, which is a weak acid, and acetate, which is a weak base, of equal concentrations. So adding sodium acetate base to NH4 plus, which is acid, of equal concentrations, and we put the increasing scale of pKa, and we will find that the reaction is in the anti-gamma direction, so the reaction is limited. Therefore, we can apply directly the formula of the pH of weak acid and weak base. pH equal half pKa of couple 1 plus pKa of couple 2 equal 9.2 plus 4.76 divided by 2 equal 6.98. Exercise 44, which of the following statements are correct concerning the buffer solution in water? First, the pH of a buffer solution is very sensitive to moderate dilution. This is not true. A is false. The pH, the dilution, did not affect or slightly affect the pH of the buffer solution. In part B, the buffering capacity of a buffer solution increases upon decreasing its concentration, and this is also false. Part C, upon mixing n mole of weak acid HA with n mole of sodium hydroxide. When we mix HA and OH minus with equal number of moles, so HA will disappear completely. So we destroy the buffer solution. So C is incorrect. We don't have a buffer solution in this case. Part D, we mix n mole of HA with n over 2 moles of OH minus. In this case, we may obtain a buffer solution. We have to calculate we have to write the reaction and put the table of conversion. HA plus OH minus gives A minus H2O at T equals 0. We have n over 2, 0. The reaction between weak acid and OH minus is always complete. So the reaction proceeds till T equal infinity and OH minus is limiting. So half of HA disappear and we have n over 2 of A minus formed. So the pH equal the pKa plus log the concentration of base divided by the acid at equilibrium. And the number of moles are practically equal at equilibrium since we don't have exchange between HA and A minus because of the weak behavior. This is the general case. So pH equal pKa, and this is a buffer solution. So the correct answer is D. Exercise 45. Consider 500 milliliters of HNO2, concentration 0.5. We don't have any Ka value given, so HNO2, no, we have Ka of HNO2 and O2 minus equal 4.5 10 minus 4. So the HNO2 is a weak acid. Calculate the mass of NaNO2 required in order to obtain a buffer solution. To remember that a buffer solution is composed of the weak acid and its conjugate base, where the value of the pH of the solution is close to pKa of the couple. So V total equals 0.5 liters. The concentration of HNO2 is equal 0.5 molar. The buffer solution pH equal pKa plus log concentrations of the base divided by the acid at equilibrium. pH equal 4. pKa of the couple equals 3.347 plus log NO2 minus divided by the concentration of HNO2 at equilibrium. But as in most cases, we talked about the weak behavior of the acid and the weak behavior of the base, so the concentrations are at equilibrium are the initial, so HNO2 equals 0.5. By this way, we calculate the concentration of NO2 minus at equilibrium, which is practically the initial concentration of NO2 minus introduced, equal 2.25 molar. So the concentration of NO2 initial equal the concentration of Na2 introduced equal 2.25, and we apply the concentration equal number of moles divided by volume equal mass divided by molar mass times V. So the mass equal the molar mass times V times concentration. The molar mass of NaNO2 equals 69 times the concentration 2.25 times V total, which is 0.5 liters. So the mass that should be introduced in order to prepare a buffer solution of pH equal 4 is mass of NaNO2 equal 77.625 grams. So the correct answer is therefore E.